Okay, so now we are being recorded. Our first speaker is Ilka Agricola from Marburg, Germany. And it is our tradition that we say a few words about our distinguished speakers. And, Ilka, I prepared the sketch about your professional life using ChatGPT. But, it lied to me. For instance, it gave me your wrong birthday. This was unbelievable because it's just a simple piece of data. But then, it corrected. And now, if I say something wrong, just please correct. But I double checked ChatGPT. Anyway, so Ilka was born on 8th of August, 1973 in The Hague, Netherlands. And she was born again now as a mathematician in the year 2000, getting her PhD from Humboldt University of Berlin, supervised by Thomas Friedrich. Then she obtained her habilitation from the University of Greifswald in 2004. And since 2008, she is a full professor at the University of Marburg, where she is also currently the head of a Department of Mathematics and Computer Science. When it comes, she is a differential geometer, and her research focuses on spin geometry and Dirac operators, special geometric structures such as G structures, connections with torsion. She works on relations to string theory and supersymmetry, on Clifford algebras and their applications in geometry and physics. Was ChatGPT correct?
Kind of. I'm not head of the department anymore, which I'm not unhappy about, I have to say. But I have enough other jobs, and yeah, for the moment, I guess that's fine.
Okay,
I may add something at the end.
So this is great.
The math part is perfect.
Yes. Okay, good. It's also worth mentioning that Ilka was the president of the German Mathematical Society in the years 2021-22, and she's the editor-in-chief of two mathematical journals, notably Annals of Global Analysis and Geometry and Mathematische Semesterberichte. Was my German acceptable?
Wonderful, wonderful.
Danke. Okay, ladies and gentlemen, without any further ado, I'm giving you Ilka Agricola. Ilka, it's all yours. Take it away.
Thank you very much. I am deeply honored to open this meeting in Benlevo. And let me add a very, very private sentence. I am very happy to meet my Polish friends online at this occasion, because I started my first summer school in mathematics was in Poland at the castle of Tuczno, which unfortunately is not a conference castle anymore. And Eva Damek was one of the organizers, and this is very long ago, so I'm not gonna say the year. So I have very fond memories of these things. And I just noticed that, shame on me, I did not double check that LaTeX wrote Benlevo correctly. So I apologize for that. I am aware that this is wrong, but LaTeX was not. Okay, so the aim of this talk is to give you a broad introduction into connections and holonomy, and why I believe that they are key concepts of differential geometry and worth knowing, therefore, for everybody, and how they have shaped research in differential geometry over the past 50 years, and what it has to do, of course, a little bit with my own work. So, just a second. Yeah, okay. So I will recall very quickly, in order not to lose anybody, what a connection is. And what quantities are going to be derived from it. I will say a little bit about why this is relevant for mathematical modeling in theoretical physics. I am, by education, a physicist, a theoretical physicist, actually, but I switched to mathematics long ago. And as a prominent example, I will show you a new look at an old theorem, which is Berger's holonomy theorem and its relatives. So there are at least two relatives I'm going to talk about. At the very end, I will give you a very glimpse introduction at where are the points where our research starts in this broad topic. But this is definitely not to talk about my favorite technical lemma. In case you want to hear these, you tell me later. Okay, so first of all, to get into the mood and the context of our work, we are interested in relations between different kinds of objects on a Riemannian manifold. So a Riemannian manifold, first of all, just to get the notation, a Riemannian manifold, just think of it as of some kind of curved space, like a banded surface. And Riemannian means that in each point of my space, I have a kind of tangent space. And on this tangent space, I have a positive, definite scalar product. So despite the fact that I am also interested in physical applications, I will always assume a positive definite scalar product, which in Riemannian geometry is called a metric in each of these tangent spaces, depending smoothly on the point of the manifold. Okay, now there are three kind of objects we want to study on our Riemannian manifolds. So first class is, I hope you can see my mouse pointer.
We can.
Okay, so geometric structures as a very broad idea. Geometric structures would mean special kind of curvature properties, of course. Or I would like to have maybe some kind of contact structure, actually an almost contact metric structure, but just speak contact structures, or almost complex structures, or any other nice geometric structures which are typically induced by some Lie group. The second field we are interested in are solutions of field equations, solutions of the Einstein equation, solutions of the Killing equation. So different kind of geometric differential equations which occur in a natural way, and to see how these geometric properties relate with the solvability of these geometric differential equations. And if we're talking differential equations, we take derivatives, and anything which helps understand the derivative better is a good tool. And this is in particular connections. So typically each kind of geometric structure has good invariant connections, invariant or equivariant under the geometric structure. And these connections, nabla, have a holonomy group, which I'm going to explain. And I will give you examples where we can see how these three things are intricately related. So here are some key features which are maybe not along your experience with analytical questions. If I'm saying I am solving differential equations, but without doing analysis. So the differential equations we're speaking of are rarely for functions, but they're mostly for spinor fields or more general tensor fields, which are always going to be sections of some more or less complicated bundle, like the spinor bundle or higher order bundles. And these bundles will depend heavily on the topological properties of the underlying manifold.
And here so first, I need global sections, right? You mean global sections?
Global sections. I'm interested only in global sections. That's right. Yeah. Right. So from the topology, I have existence of certain bundles, maybe or maybe not existence of global sections. Sometimes, right, I already know that they can't exist, then I'm done. But the spinor bundle typically, because it's very high dimensional vectors bundle, does have global sections, and then I'm interested in special solutions. Okay, the equations we are interested in are highly overdetermined. So solutions are only going to exist in exceptional situations, and in fact, not on all manifolds. The manifolds which we are talking about will be required to have certain special symmetry properties. And therefore, actually, I am not only interested in finding the solution, but I'm also interested in finding the right manifold on which the solution is going to live. So finding the manifold is part of the exercise. And so from these things, typical analytical methods are not going to work. I do not have like a local existence theorem in a local neighborhood of some point. There always exists a local solution or something. Now, if we're speaking symmetries, what symmetries would be natural to consider? The obvious thing is to look at isometries, meaning maps preserving the metric. Whenever I have a metric, in particular, I have a notion of angle and length. And so with any manifold, I can associate the isometry group of the manifold diffeomorphisms from M to M, which respect the metric, right? This is a good idea, but actually we can do more than that. So there is a second symmetry concept, which has turned out to be crucial in differential geometry. So around the middle of the last century, there was the discovery and use of a second important symmetry group, which is called the holonomy group of a manifold. And the holonomy group is interesting because it relates in a very sophisticated way the connection to curvature and solutions of equations as I'm interested in. Okay, so let's try to understand what the holonomy group of a Riemannian manifold is. And so we start at the beginning, very, very, very beginning. We go back to our first term, calculus. So we call in calculus, you learn the directional derivative, right? So I take a function f from Rn to R, smooth, fix a point x naught, choose a direction u, and define the directional derivative of f in direction u at the point x naught, just by this limit. And since my function is smooth, actually that's just the total derivative of f evaluated at x naught applied to u. Now, if I have a vector field v, then I can just define the derivative of the vector field v in direction of the vector field u component-wise by the formula above. So we have a notion of taking derivatives of vector fields in directions of vector fields. Okay. If we take vector fields which are just coordinate derivatives, then of course second derivatives commute. Right? So nabla v, nabla u, or nabla v, nabla w is the same as nabla w, nabla v. And these vector fields, of course, commute. These things are not going to hold in general anymore. Furthermore, for this very naive calculus directional derivative, we observe that it's compatible with the scalar product, meaning the derivative in direction v of the function, which is the scalar product, just standard Euclidean scalar product of two vector fields, is the same as taking derivative in the first component, direction v, x, and then scalar product with y, plus x derivative in the second component, right? So there's a kind of product rule for scalar products. Okay, and these are properties I want to keep. Now back to more roots, which is Gauss 1827. So Gauss observed that, unfortunately, on surfaces, the directional derivative of two tangent vectors is, in general, not tangential anymore, right? So think of a surface embedded in space, take two tangent vectors, take the derivative, just as I told you to do in calculus, then it's not tangential anymore. So this is not a way of defining a derivative which would stay in the tangent space. And the solution to that problem is very easy. If it's not tangential, you force it to be tangential, meaning you project down by brute force to the tangent space. So here's the picture to have in mind. Here's our surface M. Here are two vector fields u and v I did not depict. In green is the tangent space in the point P, T, P, M. The derivative in general will not be tangential, but I can project it down by orthogonal projection because I do have a scalar product. So I can end up, I force it down to the tangent space. So a connection abstractly is going to be some kind of abstract derivation rule on a manifold, satisfying all the formal properties you would want to have from a directional derivative. It is a derivation, you know how to plug out functions and multiples, and connection applied to a tangent vector field should again be a tangent vector field. And so the example one can cook up is just to take the projection, which I will denote nabla little g typically, in order to recall that it depends on the choice of metric, right? Of the directional derivative to the tangent plane. And this actually by now goes by the name Levi-Civita connection, okay, and can be defined on any Riemannian manifold. Now, the act of forcing the derivative to lie in the tangent space means that I have a difference term, right? Here is the Levi-Civita connection. Here is the original directional derivative. So the two are related by something, and the something is what is called the second fundamental form in differential geometry. And it turns out that this map, big Roman 2, is actually symmetric in U and V. So the second fundamental form catches, actually, you can view the second fundamental form as something which kind of annoying, right? Because it's the term you have to deduce in order to be tangential. But you can also view it positively in the sense it certainly will carry some information. And what is the information? Well, in the case of a two-dimensional manifold, just the surface in R3, right? The second fundamental form, Gauss realized it has very nice intrinsic meaning. So the determinant. Question?
Sorry, I have a question. So, in order for this story, using this projection to make sense, you really want your manifold, at least in this case, to be embedded, yes, in a larger space.
Yes.
Okay.
Yeah, that's right. In the end, Levi-Civita connection exists without embedding. That's true. But for the purpose of the talk here, to start at the moment, I'm still embedded. Yeah.
Okay, thank you.
But an abstract connection is then something which does not require an embedding because it's just something which formally behaves like a connection. Yeah, thank you.
Thank you.
Right. So, but that's the right question, because obviously we want to distinguish intrinsic from extrinsic properties. So the surprise is what is called the theorema egregium of Gauss, right? That the determinant of the second fundamental form, despite being defined via an embedding, is actually an intrinsic quantity, which does not depend on the embedding. It's the so-called Gaussian curvature. Whereas the trace of the second fundamental form is an extrinsic quantity. It's basically the surface energy tension. And in dimension 2, it's just called the mean curvature. So what do we see? Well, so we see that even if an embedding is used to define that, we apparently have intrinsic curvature quantities, extrinsic curvature quantities. Intrinsic quantities can be generalized in such a way not to be independent of the embedding, but actually of not requiring an embedding. And both quantities, despite being a kind of curvature, were defined using the derivative. So this is what connections will achieve later as well. Curvature is a derived quantity from connections from derivatives. And here are some pictures I took during one of my differential geometry lectures. You can see a very typical German lecture hall in the background. So the minimum of the extrinsic curvature, the mean curvature, vanishing mean curvature, these are just minimal surfaces. And the soap bubble did not study mathematics, but nevertheless, it knows exactly what form to take to achieve the zero surface tension for our soap bubble forms. And the different forms, so the square, the tetrahedron, and so on, is just the boundary conditions for solving this highly non-trivial differential equation. So we did that in our lecture, and it shows you, well, differential geometry course is fun, right? Okay. Now, Élie Cartan, much later than Karl Gauss, realized that the Levi-Civita connection, as useful and beautiful it is not the only possibility. But it is actually possible to modify connections to satisfy the same properties as a directional derivative by adding extra terms. One example of that you may know from a course in theoretical physics. Namely, in electrodynamics, there's a lot of hand-waving done to kind of justify that you should introduce an additional term depending on the potential to the normal directional derivative. So in physics, the notation would be like derivative in direction mu is the normal partial derivative up to coordinate mu plus some constants E, H bar, and then the gauge potential, the components of the electromagnetic potential. And if you write it in mathematical terms, that's just what it means, right? Evaluate A on U. That's basically, so here it's written as a vector field, but then it's just the one form. The one form applied at U is a function, and then you multiply it with V. So this is the first thing, and this is indeed a U1 gauge theory lurking behind. So a first indication that for some applications, more general connections would be useful. Here's another very easy example, which actually I give my second-year students just to show them that the world is not as easy as they might think. If you go in dimension 3, just R3, no curvature, nothing at all, and you define a new derivative by saying take the directional derivative plus the cross product of the two vector fields U times V. Then this gives a new term, and the funny thing is that they will then check that it fulfills all properties a directional derivative should have. Right?
Sorry, I have a question.
Yes.
I'm a little bit worried about this H bar in the denominator.
Why?
Since the story is classical at this moment, yes? H bar
Yeah, but
look like something quantum.
I don't think I got the constants wrong. No, I mean, even U1 gauge theory already uses it because it's embedded into a context of special relativity. It appears already there. I will check by constant, but I'm pretty sure that is correct.
Okay, thank you.
I can check. Yeah. Okay. Now let's go back to this one. This, for example, was already written down by Cartan, okay, who interpreted this additional cross product term as kind of an internal angular momentum of space. And that's where the word torsion comes from. He thought that space is tordu, bent. And this just in French is torsion is the word to use for that. So, right, because even if the derivative vanishes in the classical sense, it will not in this distorted sense because of the additional term. And in fact, Ilka proved that there are 3 types of torsion. Namely, it can be given by a vector field, or one form, which is like the first case. Or it can be skew-symmetric, which is like the second example. And then there's a third component, which does not have such an easy interpretation, and therefore I'm not going to explain it today. Okay, good. So here is Élie Cartan, the godfather of all of differential geometry and connections and holonomy. So in one of his articles, he says, what you should do is, given a manifold embedded in affine or projective or conformal space, attribute to this manifold the affine or projective or conformal connection that reflects in the simplest possible way the relations of this manifold with the ambient space. Now, we don't need ambient spaces anymore, but his geometric intuition was guided by that case, just as with Gauss defining the second fundamental form, right? But the idea is still the same, namely, the manifold has some kind of geometry with which it comes. And the best is to find a connection which is adapted in the best possible sense to the underlying geometry. This concept has turned out to be extremely successful. Now, curvature and connections. Suppose now we are given a connection, so forward derivative rule on a smooth manifold. I take 3 vector fields, x, y, z. So let me explain you how to get to curvature from the connection. Well, the first is the most general, the curvature transformation. Curvature transformation is defined as R of 2 vectors x, y applied to z. So it's the operator nabla x, nabla y. applied to Z, minus, in inverted order, nabla y, nabla x, minus nabla commutator x, y, z. And if you recall what I wrote on one of my first slides, on this calculus slide, it was that for just directional derivatives of coordinates in flat space, nabla xy equals nabla yx, and the commutator vanishes. So in this particular case of calculus in flat space, we do not see curvature because it vanishes identically. Right? These two terms cancel out, and this term is zero. So curvature is something we do not see in the Euclidean vector space case we learned first at the university. Now, this is a rather complicated 3-1 tensor field. So we contracted twice to get more tractable informations, but of course we pay a price because we lose part of the information. So the first is the so-called Ricci curvature. The Ricci curvature is the trace of the operator which to x assigns the curvature r, x, y, z. Okay, so from x to that. And nabla, just, I sometimes put it, sometimes I don't, just to make sure that we are aware that it depends on the connection I chose at the beginning. And then the Ricci curvature being a endomorphism field, now I can take again the trace, and then I get a scalar function on the manifold, which is called the scalar curvature. And the Gaussian curvature is just a the scalar curvature is the generalization of the Gaussian curvature we had seen before. Now, a connection is called flat if all curvature transformations vanish, and it's called Ricci flat if the Ricci curvature vanishes, which of course is a weaker condition. Now, you will agree with me that this is 100% correct definitions as in a differential geometry course. The problem with it is a bit that the way I present it here, it's slightly uninspiring, to be honest, right? Because the definition does not convey an intuition how to work with these quantities, but they're so crucial that actually a bunch of time in any differential geometry course is spent on understanding, getting a feeling for these quantities. Because if we look at the vacuum Einstein equation of general relativity, it just says, well, space would be a manifold with Ricci curvature vanishing. Now in Lorentzian signature, but besides of that, all the definitions are the same. So Ricci curvature vanishing or not vanishing would be the most important property of space. And that tells us it's worth investing time understanding Ricci curvature. Right? In the model underlying general relativity, the metric actually is interpreted as being the gravitational field. The Lagrangian is then just the integral over the scalar curvature. Okay, so the definition of scalar curvature already enters the physics here. And the Euler-Lagrange equation of that functional, well, this is just the Einstein-Hilbert functional, is just the Einstein equation, again, on our unknown manifold M, right? So does every manifold admit a Ricci zero, Ricci vanishing, Ricci curvature metric, and so on? That's the actual question here. Okay, so that's how we get from connections to curvature. Here is some philosophical comments, right? We are interested in curvature and connections, but if we just go blindly anywhere, we will not end up anywhere. So I would like to try to state a bit what kind of problem we actually want or need to solve. So what are the challenges? Well, so tangent spaces in different points of a manifold are a priori independent of each other, in particular if we do not have an embedding. Now, taking derivatives or describing curves requires moving between points, and therefore between tangent spaces. And while we're moving between tangent spaces, all quantities we're looking at should be kind of invariant, meaning independent of the choice of coordinates. right? We do know that in any point, a manifold has a small neighborhood where it behaves like Rn with some kind of local coordinates, but I don't have a canonical choice of coordinates. And so the fundamental concept, which is kind of hidden behind connections, is actually that of parallel transport of vectors along curves. So parallel transport. This is Levi-Civita's original definition of a connection. You take your manifold and think of a curve gamma between 2 points P and Q on the manifold. Then he says there exists a unique map P gamma, so depending on the curve, which moves from the tangent space in P to the tangent space in Q. So the image of the vector field Vp under P gamma, I call VQ, right? So this moves, and think of the point Q moving on the manifold. So you have the starting point P, and as you move along gamma, your point Q progresses along the curve. So my vector V moves with the end point of the curve Q under this map P gamma. And this is going to be called parallel along the curve gamma if, so the old-fashioned notation is nabla V S ds equals 0. And as an abbreviation, I just write nabla of the vector field V in direction of the tangent vector of this curve is equal to 0. Okay, so all derivatives of my vector field vanish as I progress along the curve. And this is particularly interesting for closed curves. So P equals Q, because I get a notion of parallel transport of vectors along curves on manifolds and in particular on surfaces. So here are the most wonderful examples actually, right? So you have your vector field V here, and here's a closed curve, which of course is a smooth-on geodesic triangle. Okay, so I take 3 great circles on the sphere and I smooth the corners, but that's kind of almost a geodesic, almost a triangle. So here's a vector field. My connection is preserved length, and therefore, as my vector field moves along the triangle, the length of the vector field stays constant. And these angles, right, with the tangent vector of the curve always stays constant. So you move along the first edge. Then you move along the second edge, and along the third edge. And the surprise is that the vector field where you end up is not the one you started with. So this is just measuring something, right? So if you would, in spherical geometry, this is a theorem from 17th century, think of it, right? That if one adds the angles in a geodesic triangle on the sphere, then the sum of angles is always larger than 180 degrees. And this is basically measured by this parallel transport. Here we have the opposite situation. Namely, we have a surface of a saddle point, right? Surface of negative curvature. And on the saddle point surface, moving again along the edge of the curve, of a closed curve, brings me back to a vector, which again is not the one I started with, but whereas in one situation, the angle is positive, in the other situation, the angle is negative. This is not totally obvious from the picture, but I hope you trust me that this is true. Okay, so parallel transport gives us a measure of how things change along this curve. And basically, it's a measure of the curvature of the piece of the surface enclosed by this closed curve. So now we generate a group by looking at all parallel transports along closed loops at the same time. And this is now holonomy. That's where we wanted to go. So we fix a point P. Consider all closed loops gamma for this point. To each of these loops corresponds a map P gamma from the tangent space to the safe tangent space. So here's again, in a much more simplified way, the corresponding picture. I have the point P, the tangent space. I move along a closed curve, and then I have a map P gamma, which maps the first vector to the second. By CP, I denote all closed loops for P. And the holonomy is now going to be the group generated by all these parallel transports, because concatenation of loops will correspond to composition of the maps P gamma. The inverse of P gamma is just the parallel transport along the same curve, but in opposite direction. So we really get a group. If now I do not want to measure topology, I can restrict my attention to contractible loops. If I look at contractible loops, then I get the notion of the restricted holonomy group. Okay. And these full and restricted holonomy groups actually, so I denote them by the holonomy in P and the holonomy in them 0, and that's not a coincidence because this is in fact the connected component of the identity of the larger group. And actually they're not really dependent on the point P, they're all conjugate. So here comes our holonomy. That's one of our largest players in the game. And now the
question.
Yes.
The independence of the chosen point is if we assume that our manifold is connected, yes?
Yes, absolutely. I'm assuming connected for that. Yeah. Right. So presumably this name holonomy is kind of derived from what is called a holonomic frame in mechanics, right? But the relation to that is rather weak, so it's kind of not used anymore. Okay. Holonomy can be computed through curvature. This is not totally surprising, but it has to be quantified. So this is one of the famous Ambrose-Singer theorems from the mid-50s. Namely, for any connection nabla on a Riemannian manifold, the Lie algebra of the holonomy group in a point is exactly the subalgebra of the orthogonal group on that same tangent space, generated by the elements. Well, take two vector fields V, W in TPM, any closed loop gamma. Then I take the curvature transformation P gamma V, P gamma W, and then conjugate it with parallel transport along P gamma. So in particular, if I know something about the curvature, I can compute the holonomy, not in an easy way, but still possible, and vice versa. Right? For example, for a flat connection, if all curvature transformations vanish, I get immediately that the holonomy Lie algebra is 0. Now, if the holonomy Lie algebra is 0, it means that the algebra, that the Lie group generated by all parallel transports along closed curves is always the same. There is no group generated. So that means that parallel transport is path independent, right? It doesn't matter which curve I choose because it always vanishes. And if parallel transport is path independent, there is tremendous consequences. For example, the manifold has to be parallelizable, right? Because you take any frame in some point, and transport it to all other points. And since parallel transport is path independent, this will define a global frame.
Sorry, just a quick question. This notion of parallelizability is the same as tangent bundle being trivial, or it is weaker?
Yes. No, that's the same.
The same. Okay,
right.
Thank you.
Yeah, right. And in particular, my manifold, I'm interested in spinors, remember? So the manifold, any parallelizable manifold, for example, is a spin manifold. So it gives really strong restrictions. And we see holonomy links to curvature, links to global topological properties. And for example,
the parallelizable manifold, right? Any Lie group would be an example of a parallelizable manifold, no?
Yes, absolutely. And indeed, a Lie group does have a flat connection, but it's not the Levi-Civita connection.
Okay.
It's a connection.
Okay, but just to be sure, we are always talking, if we are talking about connections, we always mean in this context connections on a tangent bundle, since you
Yes.
can also consider other different vector bundles, and it could happen that you have some non-trivial, non-parallelizable manifolds, but still there could be some bundle which admits flat connections. So we are not in this context. We always restrict ourselves
Yeah.
to this tangent bundle. Okay.
Right.
Thank you.
We are also looking at other bundles and induced connections, but my connections typically, most of the time, are coming from the tangent bundle, so they are fine connections. So that's why I'm talking connection on M. I mean, connection on the tangent bundle.
Okay, I want to be sure. So if the manifold with G is parallelizable, then this means that for any gamma, the transformation P gamma is the same?
Yes.
Okay.
Yeah. For the Levi-Civita connection. I mean, you could take any other, you have a choice of connections, right? That's why here there's just an application in this direction. For the other direction, I have to say in detail which connection I'm looking at. But it is true, even if I have a flat connection, which is not the Levi-Civita connection, the manifold has to be parallelizable. And so actually something we did at some moment was to classify all manifolds which admit a flat connection where the connection is metric, but with a certain type of torsion, namely the skew torsion. And the answer was exactly, so what parallelizable manifolds come to your mind if I ask you, give me an example? Lie groups presumably will be one of the first examples you think of. And then I'm saying, okay, I want an example which is not a Lie group.
Sphere.
Right, which sphere?
S7 maybe.
S7, exactly. And so the theorem is exactly a manifold admits a metric connection with skew torsion that is flat if and only if it is a sphere or a 7. Right. Now, to give interesting examples of not a sphere and not a Lie group, some Stiefel manifolds, for example, would be nice. And so, nevertheless, they do not admit the canonical connection on a Stiefel manifold is not flat. Okay. But yeah, so
I'm not so sure whether I understood you correctly. So how about torus?
I'm only interested in local. I do not measure connection. I do not measure topology. I'm assuming simply connected, even though it's not written. Yeah.
Okay.
Yeah. So of
So
course, I mean, all kind of. Yeah, I am not interested in Bieberbach manifolds of that kind. Yeah, that's right. Yeah. I mean, I can modify all statements to include that, but I didn't want to do it. That's right. Okay. Good. So here comes finally Berger's holonomy theorem. So I'm presenting the version by Jim Simons from the 60s. So the restricted holonomy group of a complete, simply connected, irreducible, and non-symmetric Riemannian manifold can be either generic, SON, or one of the groups listed below. So the dimension can be divisible by 4. Then the restricted holonomy is SPn times SP1, which is a quaternionic Kähler manifold, or SPn, which is a hyperkähler manifold. A quaternionic Kähler manifold is always Einstein, whereas a hyperkähler manifold, just the little difference of having this SP1 factor here makes it actually Ricci flat. Dimension can be divisible by 2. Then it's a Kähler or a Calabi.
I don't understand this notation. SPn times SP1, or should be divided by?
Yeah. So no, times SP1.
Yes.
No quotient. SP1. So I embed SP1 into 4n-dimensional orthogonal group in a very specific way, and then I just take products of these group elements.
Okay, just products. Okay.
Just products, right? It's not a direct product. So you have some elements which multiply to identity, or despite the fact that they're not the identity. Right? But it's really product, but one has to specify how this embedding into SO 4n looks like, which I'm not doing. No? Right. RSPN. the hyperkähler case. In even dimension, it can be holonomy group, restricted holonomy UN, a Kähler manifold, or SUN, a Calabi-Yau manifold. Again, Kähler manifolds do not even need to be Einstein, whereas Calabi-Yau are always Ricci flat. And again, there's only this U1 factor, which is the analogy of this SP1 factor here, right? Which makes the whole difference. Dimension 7, it can be G2. And in dimension 8, it can be spin 7. And in all these situations, there are some parallel objects, whereas for the quaternionic Kähler manifold, there's a parallel distribution, which I'm not going to describe.
Sorry,
right, but here we have a... Yeah?
Sorry, could you quickly explain this notion of being irreducible and non-symmetric?
Right, so irreducible is a manifold, so not locally a product, and non-symmetric means not a symmetric space.
So not being a quotient of a group, yes, by some.
Well, no, it can be homogeneous. It could be homogeneous, right? But not a symmetric space. So not a quotient of a group by the stabilizer of an involution.
Okay, okay.
All right, but not a symmetric space. Yeah. Okay. Now, manifolds covered by.
Question. Could you come back to the? Yes. So if dimension of M is odd, then the group is SON?
If it's compact, yeah, complete, simply connected, irreducible, non-symmetric, it is either G2 or SON. Yes.
Okay, so because here you listed just some even numbers and 7, 8. So if n is odd, then will be SON, provided other assumptions are satisfied.
Yeah.
Okay.
So, and it shows you exactly the problem with this list. The problem with this list is that it says, well, actually, in most cases, it's going to be SON, because this is a very short list and very special types of manifolds, right? So in most situations, the Riemannian holonomy group is actually not going to be useful because they will be of generic type SON. And only in these very special geometries, you get something beautiful. But what if your manifold is not one of the type in this list? For example, if you look at odd dimensions, all contact manifolds, all almost contact structures cannot be detected by looking at Berger's holonomy. And the idea of modifying the connection is exactly to allow to treat manifolds which cannot be detected by the Levi-Civita connection, right? So this really gives us the first clue. Now, manifolds with this holonomy are called of special or integrable holonomy. Berger proved that the groups on this list were only possibilities, but he could not show whether they actually occurred. And in fact, the existence of metrics of all these holonomy types was like a huge research program for differential geometry. So Yau, with the solution of the Calabi conjecture, was able to show the existence of compact manifolds with metrics of holonomy SUM and SPM, so hyperkähler and Calabi-Yau case. The explicit construction of non-compact matrix with holonomy G2 or spin 7 is due to Bryant and Salomon 1989. And compact examples of manifolds with holonomy G2 or spin 7 were only constructed by Joyce 1996. So in that sense, this theorem was really a work program. And what I'm now going to do is I'm going to relate this list to the existence of parallel spinners, right? Which is one of the simplest differential equations we would want to solve. And I'm just putting here the question, what if a manifold is not any of these? Well, the answer is follow Carton's philosophy, define a new connection such that it's more adapted to the geometry where the Levi-Civita connection obviously is not. So here comes Wang's theorem on parallel spinners from 89. Suppose you have a complete simply connected irreducible Riemannian spin manifold. Of course, otherwise I can't speak about spinners. and denote by n the number of parallel spinors, and assume that it's strictly larger than 0. Then it has to be one of the type of manifolds listed below. And here I reproduced Berger's list, and I crossed out the 2 cases which actually are not allowed. Quaternionic Kähler manifolds with SPn times SP1 holonomy, or Kähler manifolds with UN holonomy. All others are fine. Okay, so it has to be a hyperkähler, Calabi-Yau, parallel G2, parallel spin 7, which in a nutshell means that having parallel spinors is even more rare than having generic holonomy SO, not having generic holonomy SON for the Levi-Civita connection. So let's try to understand why the answer is exactly what it is and why these 2 cases disappear. So there might be topological reasons for these cases not to appear. The first one is that Kähler manifolds are always spin C, but they don't have to be spin. So they clearly cannot always have parallel spinors. However, quaternionic Kähler manifolds are spin, and nevertheless, they do not admit parallel spinors. Here is a curvature reason. Namely, one easy argument shows that if there exist parallel spinors, the Ricci curvature has to vanish. So now again, it's this baby example of solution of a differential equation implies a curvature condition. So let me show you very quickly how the argument goes. It goes by what we call an integrability condition. For any spinor field psi in the spinor bundle of a Riemannian spin manifold, we have a nice identity relating the Riemannian curvature operator to the Ricci curvature. Ricci curvature Clifford product with psi is equal to n being the dimension of the manifold, of course, minus 2 sum over an orthonormal frame, EK, of curvature transformation R evaluated at x, comma EK, this is the same x, right? Now it's the curvature in the spinor bundle applied to psi, Clifford multiplied with EK, sum. Now,
sorry, a stupid question.
yes.
What is this capital N?
Capital
Number
N,
of spinors.
number of parallel spinors.
Okay, okay.
Big
Okay,
N
okay.
is
Yeah,
the
thanks.
number of parallel spinors. Yeah, fine. So supposing we have parallel spinors, we have always this identity. Now plug in your parallel spinors. Suppose that N is larger than 0. Then have a solution of nabla psi equals 0 where psi is non-trivial. That means that all these curvature operators applied to x psi vanish by definition of curvature because it just iterated derivatives, right? So then it means that the right-hand side vanishes. So I have a non-trivial spinor such that Ricci times spinor is 0, but Clifford multiplication is injective, and so we conclude that the Ricci curvature vanishes. However, now this is a totally correct argument. However, my favorite argument is what we call a holonomy principle. Namely, if I have a connection which preserves a section of some nice global vector bundle, for example, my spinor field.
This question may be a bit stupid, but how do you apply Riemann curvature to the spinor?
No, I do not. This is the formal definition of the curvature operator, just as before, now applied to sections of the spinor bundle instead of sections of the tangent bundle. So this is, this is nabla x nabla ek psi minus nabla ek nabla x psi minus nabla commutator x ek applied to psi. But there is a deep thing here. Any connection on the tangent bundle induces, by principal fiber bundle theory, a connection on any associated vector bundle, and the spinor bundle is an associated vector bundle. So Levi-Civita connection from tangent bundle carries over to Levi-Civita on spinor bundle. And the curvature operator on the spinor bundle on the right-hand side indeed is linked then to the Ricci curvature, which is really on the tangent space on the left-hand side. So there is a non-trivial calculation really behind this identity, and there's an understanding of how the connection is being transported to the spinor bundle. So it's not a stupid question at all. It's actually the right question to ask. It's just I was trying to hide it under the rug for time reasons. But you're right, right? Now let me wrap it up. So for the holonomy principle, if a connection admits parallel objects, the holonomy of the connection will be in the stabilizer of the parallel object. And then one checks that the generic stabilizer of a spinor, depending on the dimension, is SPN, SUN, G2, or spin 7. Therefore, the holonomy of the connection I'm looking at has to be inside any of these groups. And then I get immediately the positive list of the cases of Berger's holonomy, which we're interested in.
And once again, this corollary is for which assumptions? That your manifold is simply connected spin, yes?
Always, yes.
And the
Simply
number of parallel spinors is strictly greater than 0, yes?
Yeah, just as here. Connected,
Okay.
simply connected, irreducible spin.
Okay,
I always CSC. Yeah. Right. Okay. Now,
And sorry, could you explain what is the stabilizer of psi?
yeah. So this is I have a natural action of the orthogonal group on all sections of all tensor bundles. So I'm asking, what is the subgroup of the orthogonal group preserving this element? Like the subgroup of U, if we are in even dimension, 2n. Okay, I don't know, does this work? Can I write? No, I don't want to say, I want to type, this is better. So, wait, so if we are in dimension 2n, oops, this is very light. Okay, and I take a enormous complex structure omega, right? Then I embed, and I'm asking, what are the elements of SO2n stabilizing omega? The answer is going to be UN in its standard realization inside O2n, right? So the structure group of enormous complex structure is always UN, and in the same vein, I calculate that the stabilizer, so the subgroup of ON, whatever the dimension is in my context, because here the dimension is 4n, here the dimension is 2n, here it's 7, here it's 8. So with the right dimension, I'm asking what is the subgroup stabilizing this as a tensor field or a spinor field.
Okay, thank you.
Mm-hmm. Yeah. Okay, good. Now you have to tell me how much over time you allow me.
Well, you have 3 minutes over time, but we can go on with questions up to 11. At 11, we have coffee break. So at 11, we have to finish.
Good. Yeah, now I just have to get back to, yeah, right. The question for our later research here is the same, namely, what if my manifold is not one of these? So again, the trick is going to be, and not today, presumably, that modify the connection in such a way that the spinor field equation I'm interested in can be interpreted as being parallel for a certain other connection. Now I want to relate all that to a third list of, I want to delete this, that's not working. Oops, okay, it stays attached now. Okay, namely, the actions of transitive actions on spheres, or how to write a sphere as a homogeneous space. And this is at the same time, not related at first sight, but if you look at the answer, you will see, oh, but it must be a relation. So suppose we have a compact connected Lie group G acting transitively on a sphere of some suitable dimension, meaning that my sphere can be written as a quotient of G mod H, H being the stabilizer of a generic point. Then there are two possibilities. Either my group G is the full orthogonal group SON plus 1, and my sphere is just the quotient SON plus 1 over SON, which is the way to represent a sphere as a symmetric space. So that is again the symmetric case. Or my sphere is written as a quotient as given in the list here. And then the dimension of G mod H is either of type 4n minus 1, then it's SPn times SP1, SPn times U1, or SPn, and then H can be computed directly, SPn minus 1 times SP1, SPn minus 1 times UN, and so on. Or the dimension is 2n minus 1, then it has to be UN or SUN. The dimension can be 6, then it's G2 with stabilizer SU3. Dimension can be 7, spin 7 over G2. And it can be 15, spin 9 over spin 7. So all these are the ways of writing spheres as quotients of groups which are not orthogonal groups. And whereas in the previous case, we basically had always odd dimensions except for, no, always even dimensions except for 7. Now we always have odd dimensions except for 6. And we see that these lists are almost the same. Now let's not look at isotropy representation. So the case SPn times U1 is definitely exceptional because it did not appear in Berger's list and it did not appear for parallel spares. It is not a surprise that these representations are so similar to the ones we had before. Because if one embeds the sphere Sm into Rm plus 1, just as vectors of unit length, then the action of G on the previous slide on this sphere is indeed not any representation, but it's the restriction of the holonomy representation on the TMM plus 1 for just matching groups from these two tables. So it is really very strictly related with it. And here comes a wonderful example. So the sixth sphere can be realized as G2 over SU3. And this is the so-called nearly Kähler sixth sphere. And it exists because it has an almost complex structure, which is not integrable, inherited from the vector cross product in R7. And the restriction of the 7-dimensional irreducible G2 representation to the subset S6 in R7 is indeed this transitive action. And the nearly Kähler structure then turns each tangent space into a complex vector space. It's equipped just isomorphic to C3, therefore. It has a J-compatible Hermitian scalar product, and it does have a nice adapted connection, which is not the nearly Kähler connection, and not the Levi-Civita connection. Now, if you want a nice reading on G2, I really strongly recommend the article by Christina Draper. By comparison, we can obtain a list-free version of Berger's theorem, which is basically due to James Simons. So that's what I call Berger holonomy theorem V2. Assume that the holonomy group of an irreducible, simply connected Riemannian manifold at a parent P does not act transitively on the sphere of unit length vectors in the tangent space. Then M has to be symmetric. Right? So the three notions are very strongly related. And one conclusion is that homogeneous spheres are kind of toy models of the non-symmetric Riemannian manifolds with holonomy as given by Berger's list. Now, since we had lots of questions, and I'm happy we had them, I will jump very far quickly to conclusions. So,
because I have to correct myself, the coffee break is in fact 10:45. I made a mistake.
Okay, yeah. So which makes it even better to jump. I will be happy to provide the slides. Okay, so if somebody wants to read the latest slides. So generalizations, I already said so. The generalization has to be allow for more general connections and actually not on vector bundles, but on principal fiber bundles, allow for torsion, and then this gives you the natural mathematical habitat for Yang-Mills theory, coupled systems, whatever you want to do. Derive the most general type of geometric field equations for the class of connections you're looking at from a hypothetical solution, deduce restrictions on the holonomy and other properties, in particular like curvature, and then construct them and then try to find nice applications. And that's exactly what I'm doing in my research group. And the details come now. And I jump to my very last slide, which is here. So thank you so much for listening. I tried to find the oldest picture I had from Bend Level. It was definitely in Bend Level earlier than 2008, but I couldn't find any older picture last night. So that's me with my son Julius, Udo Ziemann, and Barbara Poster in 2008. I hope you enjoy your time. I definitely always had a great time in Bend Level whenever I was there. We're organizing a differential geometry conference in Bend Level next year. So if anybody now has won a taste of differential geometry, hey, let's meet in July in Bend Level again. I'd be happy to meet you there. Co-organizers are Alex Citrale and Alexandra Brovka. And that's it. So thank you very much for listening.
Thank you so much.
Thank you.
And now there's 3 minutes for questions before coffee, if any remain.
We have a 45-minute coffee break, so let's take this opportunity and discuss a little bit. You see, I'm actually quite involved with the holonomy. My first published paper was about holonomy maps. And so I was wondering if you could touch upon issues which are very important in the context of studying holonomy. I'm sure you know this Kobayashi reconstruction theorem. If you have axiomatically given holonomy map, so you simply take loops on your space, manifold, say, and you have a bunch of obvious axioms which are satisfied by the usual holonomies which are constructed exactly as you described. More in the sense of a principal bundle, then actually given such a holonomy map, you can always reconstruct a principal bundle with a connection on this principal bundle. And then, of course, this principal bundle with its connection will give you exactly the holonomy map you started with. So this is one thing that maybe you would like to comment somehow upon.
Yeah, we agree. This is the right context to explain things. Principal fiber bundles are the right context, right? Mm-hmm. So this reconstruction from understanding what is a connection on a principal fiber bundle and how to have this one-to-one correspondence to all vector bundles that one might, or associated bundles actually, when one wants to consider. So yeah, this is powerful. If there is some philosophy I learned over the years, one is work with principal fiber bundles, not with vector bundles. Mm-hmm. Principle number one. Principle number two, if a manifold has extra structure, then there is a reason for it. Like an almost contact structure, like certain curvature properties, like an almost complex structure, or these homogeneous spheres. So the question is to detect the extra structure by using our machinery of holonomy connections and so on. And usually this is always successful, and it gives us a much broader range of manifolds than just those covered by Berger's theorem. And I have a lot of induction in the sound. I hear myself double, triple. Only now. Okay, so this list-free version of Berger's holonomy theorem, saying if it's transitive, then it's not symmetric. This is actually the holonomy theorem which generalizes to more general situations. Because the problem with Berger's theorem is it's more beautiful, but finding a holonomy theorem for other types of connections turned out to be very complicated. So that's the recent work also which has been done in our group recently and by colleagues all over the world.
Okay. Another point which I'd like you to comment on is this famous Aharonov-Bohm experiment in physics, which exactly shows that from the physics point of view, if you look at connections, the field, this is not measurable because we can gauge it. On the other hand, the curvature, which is the field strength, you can say that's what we measure. But this is what you can see that is not exactly true, because if you have your double slit experiments and you send your electrons, if you make puncture your manifold by putting a solenoid inside with magnetic field, then your manifold is kind of punctured. It's no longer simply connected. The field strength around the solenoid is zero, so the curvature is zero, but the electrons feel it. They feel the holonomy. So actually what you measure experimentally is the holonomy of this electromagnetic field, neither the curvature nor the connection.
I could not agree more. If we had more time, I would have explained this experiment and taken it as a proof that holonomy is a measurable quantity.
Okay, yes. I'm very happy. Now, one last thing, could you please go to the slides where you have more empty space?
Okay. Like here?
Yeah, it's fine. You see, in non-commutative geometry, connections appeared almost immediately. Instead of tangent bundles or vector bundles, we took the global sections, and as we know by famous theorems, we can think about them as finely jointed projective modules. So it was absolutely immediately proposed by Alan Kohn that if you want to have a concept of a connection exactly the way you were talking about, you just take this finely jointed projective modules of global sections, can be your tangent bundle, can be a vector bundle. For us, it's just a projective module over a sister algebra. And then you have this map nabla, which is our connection, okay? I'm routing with a mouse because the pen doesn't work, so please bear with me. And what you map it to the same projective module, and you tensor it over the algebra of functions on your manifold with differential forms.
Yeah.
And it completely agrees what we are talking about. Simply, you would write here an additional x, but instead of writing this addition x, we write a form here. And you go from a projective module to projective module because you contract one form with a vector field, which gives you a function. And this is a tensor product of a function. So this is why you go from sections, from vector fields to vector fields, or sections of vector bundle, sector vector bundle. But it's very easy to axiomatize this, call it a connection, and study connections in that sense. In fact, one of the first early papers, not first, but early papers on non-commutative geometry by Kohn and Riefel was precisely studying connections of that sort and moduli spaces. And you can make it in the context of Yang-Mills, and you can make sense of what it means that it is compatible with a metric. You have some Hermitian scalar product and so on and so forth. So this was my comment to your story. But we have this very big issue. We don't really have, in non-commutative geometry, we don't really have holonomy maps because we don't know what loops are. We don't know what curves are. Okay.
Yeah.
This is a big problem, but it's very fascinating because the concept of a connection and the principal bundle, associated bundle, we have all this, okay, in quite full generality. Curvature we also know a lot about, although it's more tricky. But holonomy is non-existent in non-commutative geometry. So this would be...
Yeah, it shows again that this is the right concept, right? I mean, for me, this means, I know these things, of course, not well because I'm not in this topic, but in principle, I know that they exist. So it confirms to me that indeed, this is an extremely powerful concept, right? A good concept in mathematics is one which leads to further research, which leads to generalizations, which are just not, I change a sign and then it's the same, but really leads to induced notions and to new theorems and structure. And holonomy, not holonomy, but connections in this sense here, as being the primary concept, have turned out to be wonderful, right? Getting so much research. Absolutely. Yeah. So that's actually why, but yes, for me, connection and holonomy, I wouldn't say that it's the same, but I do admit it's very close. Certainly being aware of situations where we have connections, but not holonomy, is something maybe I should keep more in mind. And yeah, probably start really have the connection. I mean, here the connection was at the starting point because it is easier,
Yeah,
right?
exactly.
Starting with the holonomy makes it much more complicated. But I do admit, yeah, I understand you don't have parallel transport, right?
Exactly, yes.
You know, this is very algebraic, and I'm not gonna become an algebraist by my lifetime. So I always admire the colleagues giving talks on that, and I listen very carefully to what they're telling me, because I have all these people who have spent some time in Warsaw, after all. Most of them, Ulrich Krämer, Istvan Heckenberger, all these people, you know well. I'm always fascinated, but sometimes I have difficulty understanding or recognizing that this is really the same thing I'm talking about. But it is. Yeah.
Indeed. Okay, so that's all from me. Let's get further questions, Alan.
And yes, I have two questions. One, probably both of them are quite general. The first one is the following. There are homotopy groups. There are also homology groups. Homotopy groups are easy to define, hard to compute. Homology groups are harder to define, but easier to compute. And how you view holonomy groups in this picture, whether they are for general manifold. Given a manifold, it is usually easy to compute or very difficult.
No, it's very difficult. It's very difficult. One needs extra information to have a, because it's very difficult to control effectively the full curvature operator. And the holonomy, if we cannot control it by the holonomy principle, like there's a parallel object or something, it's very difficult because the Lie algebra. So we compute the holonomy Lie algebra really by the Ambrose-Singer theorem, by getting everything which is generated by curvature. Now, the other picture would be to say holonomy is generated by curvature and derivatives of curvature, but that doesn't make it any easier because taking derivatives of curvature is awful just as well, unless you are on a homogeneous space where you control the derivatives, and then it's easy. It's kind of iterated commutators, basically. It's still not easy to compute, but it's feasible, right? So, yeah, so in that sense, holonomy is easy to define. I think it's more of the homotopy group type. Easy to define, difficult to compute, and even more difficult to compute. So easier, slightly easier if it's not any connection, it's a connection adapted to the geometry, right? We're not looking at any connections. We really want them to fit with the geometry. I will be cheating here and just give a very easy example. Yeah. Right here again, if you take the situation of nearly Kähler manifolds, then the crucial point is that Alfred Gray realized that there exists good adapted Hermitian connections, and working with these connections, which then have torsion, but then this is the connection. The manifold is nearly Kähler, so it's not Kähler. So from the Berger type of view, it is of generic holonomy SON. But for this adapted connection, the holonomy is going to be inside SU3. And then I have structure, and then I can work.
Okay, thank you. And one more question, sorry, if you could go back to the slide where you have, probably it was the second Berger list, where the dimension 15 appeared. Could you somehow comment for the reason? You somehow on the other slide alluded to the exceptional case of dimension 7, that maybe it is related to this octonionic structure. And how about this dimension 15?
Yes.
As I recall, it was on some slides.
Yeah, it was. I have to go back to the beginning because it somehow now doesn't let me go back. I have problem with my cursor, which does not, perhaps here. No. Sorry.
Yes, you have here a 15-dimensional sphere, and also on the second Berger list.
Here, this one?
Yes, exactly.
Yeah. So first of all, indeed, dimension 15 was in the original theorem of Berger. because Berger's theorem, as I explained, is only a list of possibilities. So, but then later there was the Alexievsky, Gray, and Brown independently proved that if a Riemannian manifold of dimension 15 has holonomy spin 9, then it is automatically a symmetric space. So the Cayley plane, basically. Okay, and since the formulation I have for the Berger holonomy theorem, here it is, I wanted if it's non-symmetric. So dimension 15 had to be symmetric, and therefore it was later deleted from this list, right? But what first thought, as I said, Alexievsky proved holonomy, Riemannian holonomy inside spin 9 in dimension 15 implies symmetric space. And since we want non-symmetric, I deleted it. But why did it appear in the list of Berger as a possibility? Because exactly there is this transitive action for a sphere in dimension 15, which is not a symmetric space. So that is funny. And understanding the geometry of this 15-dimensional sphere here is actually something we are currently doing. This is what is on my very last slide. Yeah, here. So here, this is, suppose a homogeneous sphere admits an invariant spin structure, then does it have invariant spinners? And the answer here is yes. We do have an invariant spinner on the 15 sphere. We realize that spin 9 over spin 7, but we do not understand well what it means geometrically in the sense of having an underlying geometric structure, some kind of octonionic, there's an n too much here, contact structure. It's something we're looking at the moment. Clearly, it's deeply related to Clifford structures and the octonionic Hopf vibration. So we hope that a better understanding of the octonionic Hopf vibration is going to give us the answer what this killing spinner actually means. Well, hopefully next year.
Okay, thank you. Thank you.
Okay, we really should wind it up within 3 minutes. So unless there's an emergency question, no, let's thank Ilka again. Thank you so much.
Thank you all and have a good week. Bye-bye.
Okay, let me stop recording.